Hi everyone, I'm Lior Sidi. I'm leading the recommendation and semantic search team in the data science at Wix. And today we're going to talk about platformized semantic search. So generative AI is amazing, right? So I believe that most of you already played with ChatGPT, ask a question, put it might be in a prompt, get some results, right? We all have done that already, hopefully. If not, so go ahead and try. And the question is, what happens if I ask a question on new data or personalized data of our company? Let's say I'm going to ask, can I use Wix e-commerce solution in another site builder outside of Wix? So if you will ask ChatGPT or Bard, they will ask, no, it's impossible. But actually, in the recent weeks, Wix have came up with a feature called headless that allows you actually to do that, right? So actually the answer is supposed to be yes, you should use headless. So actually, we see a lot of hallucination. We cannot really control because it's a black box, the model itself. The data is not up to date. We cannot really, as for today, we're using out-of-the-box LLMs, large language models. We don't have any tools as developers to really improve them, right? And this is not new. So already in 2020, Facebook came with an approach which belongs to the open domain question answering world, which is called Retrieval Augmented Generation, RAG, and it's basically combining retrieval capabilities together with generative capabilities in order to improve the answers, right? So how many of you have heard about this concept? Please raise a hand. Okay, cool. So it goes like that. So first we actually take the question and give it to a retriever. In our case, at Wix, we call it semantic search, but maybe you know it as any search database or a dense retrieval. But for today, we're going to call it semantic search. We retrieve some documents that are relevant for the question, and we actually put them in the context of the prompt. So now we have the question in the prompt. We have the question itself from the user, and we push inside also paragraph or textual information of where the answers should be, right? And this all together, we can actually bring the Wix headless article that we have in Wix, which is up to date. We can put it in the prompt. The LLMs eventually knows, aware of this type of evidence, and can generate an answer and say, show, just use headless. So today, we're going to focus about the retrieval. So this is the session. I'm going to talk mainly about the retrieval phase, not the generation part. And in the retrieval, of course, now I gave an example for LLMs, and generating answers, but actually you can take it for any search world that you have for retrieving documents, for retrieving website, whatever search mechanism you have. Okay?
Is it the same Bing is doing?
Again?
Bing is doing
Yeah, many, I don't know if it's exactly the same, but
I tried today, so
yeah,
I got
yeah.
from them a list of documents.
Yeah, and sources, yeah. So this is the go-to approach today. So today, if you go ahead and search for how to do that, there are tons of tools and database that will allow you to integrate retrieval mechanisms and databases with your LLMs. And even if you search how to connect ChatGPT together with retrieval mechanism, you can use LangChain, an open source library that actually have everything connected and wrapped up for you. Okay, so you can use, in this case, there is a ChromaDB connector, and we see already many developers out of the box starting working directly and retrieving data. Okay, and retrieving data and improving LLMs, or overall. So why we are here? If everything is already set up, okay, everything is ready, everything is out of the box, you can say. So the search is ready, everything is out of the box. So why we are here? So what we do see is that we do get the end-to-end experience. Everything works, everything is ticking. But if you look under the hood and you again look at the results are suboptimal. Some also developers might use traditional search that we're going to cover as well. And it's still a black box. If you use out-of-the-box search mechanism without ability to really improve and iterate, so you're still stuck in the minimum optimum, like of where you can take your platform to the next level, right? So if you get bad results, you don't know really what, as a developer, you don't know what to do. So Wix actually identified the concept of semantic search and retrieval with embeddings that we're going to talk shortly already a few years ago, and established the infrastructure team that we're going to talk about them as well, and a data science team that is focused on semantic search, full of data scientists and algorithm engineers that knows how to develop customized models around that. And so we apply some research, more applied research, develop methodologies, and create impact across Wix with these engines. And actually, this is what we are going to focus today. A bit about background and history, some methodologies, how we are doing it at Wix, and some use cases, real-world use cases that we are doing at Wix that you can actually go to wix.com and see them already deployed and having an impact. Okay? So let's start with some history and some foundation. I know that probably some of this information is already known. I will ask action. I will appreciate if you can give a direct feedback. Okay, so the concept of information retrieval flow as a framework is very simple. I think most of you should know that as developers. We have the indexing mechanism that happens offline. It can happen on daily basis. You have a document or different entities you want to index in your database. Index is basically the mapping between, for now, let's say, between keywords and the documents themselves, some way to represent the document in the database. And the querying part is more online, is when you have a user that query the database, you apply some logic here and return relevant results. Two phases, okay? So these two phases are going to be repeated through this session as well, several times in different concepts. Okay, so traditionally, we had, it's already ancient history, we had the term-based search, which is the go-to. If you know Elasticsearch, this is like back then, and Solaire, this is how it's been done. Let's say you have two documents. One document is coffee isn't my cup of tea, and chocolate man and coffee. And what basically happens with term-based search, we actually work only on the term and the text level, the words themselves. And what happens behind the scene is we address it as a back-of-word task. We eliminate stop words. We apply some tokenization, pre-processing on the text, and create this very sparse matrix of document as rows and terms as columns. And eventually, the column size is our vocabulary size that is around 30 to 50,000 words. What makes it sparse? Okay, sparse by most of the numbers here are zeros and few are ones. Okay, so this is a way to create sort of an index. You might refer it as in another formulation as an inverted index, but this is a way to represent in the old methodology. Now, in the second part, so this was indexing. Now, in the second part, we are querying. So we have a query, coffee and tea brands. We want to search the relevant articles. We applying the same processing of removing stop words, taking the words that exist in our vocabulary, searching for the articles that these words appears the most, and we have sort of ranking mechanism or scoring mechanism that score between the documents. Okay, so document 1 is more relevant for this query because the terms appears more. Okay, it's very straightforward. So this is already available with the algorithm of sort of TF-IDF and BM25, works very well on different engines. What we basically get here as a performance level, we get here very high precision. The top results are very accurate. So if the user asks for some terms, we actually get it. It's very good for cold start, meaning that if you don't have historical data, you don't want to learn from interaction, it's very good. And it's really easy to understand. You understand why you got the result. So these are main advantages we have with this term-based search. But we do have some limitation. We do have what we call a recall performance issue, where, for example, we saw on average in many production systems that in 30% of the cases, we don't produce any results at all, which is a bad experience. And also, if you do want to improve iteratively this database, you need to create term expansion, you need to create synonyms, keywords to have a lot of manual work to support also multilingual. So it's a lot of manual work in order to create improvements. Okay, so this is where semantic search comes into the picture, okay? The goal is actually to increase recall, work on unstructured data, not limit ourselves only on text, but also work on images and other type of entities we have in our data. And train it on business KPI. You might also know it as dense retrieval, embedding-based retrieval, vector search, neural search. So it's all the same. We just call it at Wix as semantic and other places as well, but it's more of all of the same. Okay, so the main concept that we need to understand around semantic search is the concept of embeddings. Who knows, who heard about the term embeddings and knows what is embedding as a whole? Please raise your hand. Okay, cool. So we divided half by half. So I will briefly go and explain what does it mean embeddings and what we're getting out of it. So embedding is the core aspect that we use in semantic search. It actually allows us to represent entities as a vector of floating points that have a meaningful meaning, okay? We can apply this representation and creating vectors out of text, images, audio, videos, and actually even complex structures like our users, website, articles. So we can create embeddings on many, many different entities. And what we are actually getting over the sparse representation, which has many zeros and ones, and the vector size is very big, here we get dense representation of a vector, which is much shorter, not on the thousands, but more on the hundreds, okay? So let's understand how it looks like. So this is a very simple example of embedding. We have here different words like airline companies, transport companies, of car companies, some celebrities, and sport companies. All of them spread on our space, which is now two-dimensional space, and we have the numbers. The number is actually represent the location, but for ease of use, let's use dots, okay? So we have each, this is what actually embeddings give us. Embeddings is the numbers themselves. This is our vector now, and this is how we now represent and represent the terms that we have. Let's say these are our documents or the items we want to retrieve. Now, the question for you is, can you identify the semantic patterns here? So there are several semantic patterns. Semantic patterns are relations that we have between the entities here, between the words, that have some meaningful meaning in our world. So do you see some of meaningful patterns in proximity, in grouping? Someone?
Clusters.
You see clusters, you see groups. Anything else? Okay, I won't give you all this time, but I did manually crafted this example. So we have, of course, the domain or clusters of domains. So we have the sport, we have celebrities. We also have proximity in interest. For example, Tom Cruise is interested in aircraft, and Michael Schumacher is interested in cars, and Rui Hachimura, which is a Japanese basketball player, is interested in sport. So we have proximity. And another thing we also have geolocation relations. So the distance between United and Lufthansa, with this United is American and this is German, is actually like Ford and BMW and Tom Cruise and Schumacher and Nike and Adidas, okay? So we have also captured in our embedding some geographical meaning, okay? And we can go along and also have transportation brand and, never ends. And as we add more and more dimension, so this is only 2 dimension and our brain can grasp only 3, but as we add more and more dimension, we actually can capture much more semantic meanings that can be used by our models. Okay, so how it's actually being used. So let's say we have indexed all these articles, and now I have a query, give me an athlete from Japan. What we are actually doing, we're taking this query and also compute its embedding, put it in the space of our articles, compute nearest neighbor, the nearest example, and take it as an answer. This is basically how it works. So also, it's not only limited to text. It's also possible to do it on images, as I mentioned, and other things. This is what actually the current technology allows us to do. The advancement that we're going to discuss now is about how neural networks are actually used to capture this essence. Okay? Cool. So before we jump into how we actually create embeddings, let's understand how it's structured as a framework. So our first part, as mentioned before, we have the indexing. We have a document, we have the document embeddings, and we embed this document on a VectorDB, okay? A VectorDB is basically what holds the connection between the embeddings and the items themselves, the documents themselves, okay? The second part is the query. We have a query from a user. We have a query embedder, which is coupled with the doc embedder that can put the query also on the same space. Also search on the vector database. The vector database basically knows how to search, apply all this KNN that we discussed before, apply all this KNN in memory or whatever technology that is doing, and producing the top K results that can also can be ranked and produce the final result. So we can, let's say, get top 300 results and then select the top 5 or top 3 if we want. Okay, so this is another flow that we use as a semantic search diagram. More specifically, at Wix, we are using Vespa. We have an infra team that maintain the Vespa clusters. It's a decision we decided to do mainly because it allows us to have a lot of flexibility and also scale. We can run very, very fast. The latency there is super fast, and we also allowed us customization in putting the embedders on Vespa itself, and a lot of customization. And we are fortunate to have an infrastructure team that actually manage it for us. So you cannot do it without an infrastructure team. It's not a team. It's not a managed service. The second capability that we have from Vespa is basically that it allows us to combine term-based results. So all the things that we had before, which is the BM25, the term-based search, we can also compute it on Vespa and eventually have a hybrid solution, a score that is built also from the term score, also from the semantic score, and eventually improve recall and precision altogether. So this is how we work at Wix. And we actually also build an internal library that wraps Vespa for our internal usage. By the way, only this week, LangChain also came up with integration, but we built something for us, and we have done some hacks to make it much easier to develop for data scientists and other developers on top of Vespa. Okay, so we talk about the framework, we talk about engineering, we talk about how to develop and how it works. But now let's understand how we actually can learn embeddings. So the progress of textual embedding, I'm going to focus now mostly on textual embedding, even though we can discuss about images and etc. But because we are in generative AI mindset now in LLMs, let's talk about text. So there is you see the evolution of embedders and technology across time. So it started with word embedding, then progress to sentence embedding, and today we already have passage and paragraph embeddings, which are much more complex. These are very big advancement that we have over time. The main contributors of these technologies are Facebook and Google that actually hold a lot of responsibility of all this research. ADA 002 is actually done by OpenAI, and it's accessible for everyone. It's out-of-the-box embeddings that you can use, okay? And dense passage retrieval by Facebook is actually also part of the solution that we showed before that is integrated with generative, and you can use it as part of the question answering mechanism. So one of the main aspects, or one of the main technology that we see across most advanced models and embedders that we have today is a concept that we call dual encoder. and we will talk about it in the next slides. So, before jumping also on the architecture, let's understand why we don't necessarily all the time want to use out-of-the-box models like ADA 002. So now you can go query OpenAI and get the embeddings. Why not? Why we don't want to use it? Once again, if you use out-of-the-box model, you do get like very fast results. You can have end-to-end solution, but once again, you have limited performance. You don't actually tune on your data. You miss a lot of information. And I think the main problem that we have is that you don't have evaluation process. This is what we actually do a lot in the data science together with the curation team and analysts that allows us to have a process of evaluating the performance of the model and then improving it iteratively with the tools that we have. Okay, and in order to iteratively improve, we can use the core technology that's used by most of the models, but there are also others, what is called dual encoder architecture. This is one of the architecture. It's very easy to explain it, but it's basically a neural network that is split to two. This is going to be our query encoder, and these are our document encoder. And basically what we are trying to do is to take pairs of query and documents that we know that are related and trying to match them together in the same space. We actually let the network to find and minimize the distance between these two entities. And we can learn this mapping as we have more and more pairs from historical data, from label data, and eventually converge to a good representation metric that we can use in semantic search. So eventually the embeddings is the output of each one of these networks. And once again, it's going back to the diagram that we have before. The document encoder is being used for indexing, and the query embedder or encoder is being used for querying. Okay? So we have these two networks that we train them together. We train them together as pairs, and after we train them, we separate them and put them in our framework, basically. And one important thing when you train a customized network like that on your business use case in order to learn patterns that relate to your business is a concept called negative samples. Some of you have heard the term negative samples. Please raise your hand. Okay, so negative samples is a way to actually, it's being shown that it's actually improved dramatically the convergence of these kind of networks. What I told you before, that is we basically take only positive pairs. So if we have a query and a document and there is a match, so basically we can learn. But we also can learn from negative samples. So if I have a query and non-relevant document, can also train the network to separate between them, right? So this is what negative samples actually do. So we want to have the distance between relevant documents and query to closer and to separate non-relevant. And the next step after we are doing that is actually sample very hard negative example. And I will give you an example here. So let's say I have a question, what is the national airline in Germany? And I know that it's Lufthansa. I have it in the label data. What we can do during training of the network, we can also take negative samples that are hard, that are very close to this question in the embedding space, or even use other search mechanism, like we had it term-based, and actually use them as negative, okay? The other approach is basically taking random samples. But if you take the hard negative and you give it to the network as negative samples, you actually allows the network to converge much better and have much better representation, okay? So I know it might be too much for some of you. Eventually, I think most of us here are developers, and we want plug and play, and we want to play with just have something solution. This is what is being done by data scientists. Okay, this is why we have a data science group. This is what we are doing. We are creating the customized networks for the company. So don't need to become data scientists today. If you want, you can, but not today. Okay. So this is a core aspect, technical aspect, and now let's move to the fun part. So what use cases we actually have at Wix? So we have tons of use cases, and this is just an example. We have semantic search for articles, which is the straightforward, and we also have for images. We also have internal tools that allow us to do site search for internal purposes. Let's say a product wants to sample some site from a certain segment, so we can do it very easily. And the next two examples that I will talk later on how actually we have done it, which are a bit more challenging, a bit more complex. First is the app market, search for application at Wix. And the second one is search for templates for creating your website. Okay, both of them, templates and application, have textual information around it, but it's a bit more tricky. Okay. So we already have in the past few years we have done different use cases. We trained custom models for some of them. Some of them felt enough that also using out-of-the-box models are enough. But overall, when we start addressing this kind of project, we have a flow in the team at Wix in general. The first is that we're creating a parity process. Okay, Vespa actually allows us to create a parity between the current solution that we have with Elasticsearch, with term-based search. So we first make sure that we put everything on Vespa and make sure that we get similar results to what we have in production. And we're applying an A/B test on that and evaluating that and make sure that we can move to Vespa, okay, as a tech stack. The second process is using out-of-the-box embeddings, not jumping, not developing, not doing too much research. It allows us to first understand how to create good chunking of the articles, how to compute distances, and really play with the data without invest too much research and data collections. The next step, of course, is fine-tuning for a specific use case, understanding the business KPI that we're trying to optimize for, and trying to create much more customized embedding. And lastly, and sometimes it's also combined with the fine-tune, we build the ranker that I told you before, or a calibration that it's actually creating everything together and trying to create boost even more this performance. What allows us actually to do all this flow is that we have a process that is constantly evaluating each version and each process. So we're doing offline evaluation, we are doing sanity checks, and every version have an A/B test. And this is totally not straightforward in companies or developers that are used to use search as just as a technical stuff. Maybe you change a search engine, you don't necessarily do an A/B test. Okay, it happens in some areas, but actually, the search has a huge effect, and we see it already, huge effect on our users. Every change in it and every version requires an A/B test and understanding what went right or what went wrong. Cool. So let's talk about in a bit more detail, just to understand how it actually looks behind the scene, how the model actually looks like. Let's start with the app market. So we have a search, and we show result. So we have historical data of query and app install. We have what the user searched. We have the app that was selected and was installed. We don't care only about clicked. We also want that the app will be installed, because this is actually a good signal that the query and the app are relevant. And we train the same model that we had before. We're training a sentence BERT, which is type, it reminds a dual encoder in sense. So we have the user query, we have the installed app, we connected to BERT networks. Unfortunately, I can't go in detail what BERT means, but if you want, please read it or read the paper of sentence BERT, and we train this dual encoder. So this is phase one, and this is dramatically improved the performance of the out-of-the-box model. The second part is even more, I think for our part it was even more amazing, is that we built the ranker, the calibrator. We actually took the same historical data and fit a model that learns how weight we want to give on each one of the scores that we got. So Vespa actually produced to us, based on the semantic and the term-based, it produced different scores, also from term-based search, like prefix boost and exact boost and text score that we have from out of the box from Vespa, and also the semantic similarity. And we want to aggregate everything into one score. So what we actually did, we took we train on this data and learn how much weight we need to give to each one of these scores, and try to predict a regressor that tries to predict the install rate, giving these scores. Okay? So this will allow us to retrieve, let's say, 30 apps and then show only top 15, or even just select apps that their install rate is more than 2%. Okay, so we can have a business understanding.
Like a logistic regression?
It's a logistic regression. It's not a logistic, it's a linear regression, even less, because we predict install rate. So it's not classification, it's regression. Okay, it's like even more this sense. What usually has been done, you take some random person and you give weights for each one, just because you feel like it. Okay, but we actually can learn the weights for each one of them. Cool. The next project is the template search. It's part of Wix funnel that you can actually search for a template based on your business or just search. And this is a bit more complex structure of the data. You can see here is an example of a JSON of how a template looks like. We have an ID, we have a title, we have an image or list of images. We have some information and description. And once again, we took the historical data between query and chosen template, and what we trained, a dual encoder once again. But here we can also add other things, like we can add clip model that can handle images. The clip model wasn't trained, it was just used out of the box, but was combined together. We also added the user segment to improve it. I can tell you that, these clip and the user segment contribute, but not contribute that significantly that we can use them. So, you need to understand the trade-off between overcomplicate your solution and, and using something that works. So you need to understand that also as an applied researcher, it's very important. So this is a very cool project as well. And, wrapping up everything. So we started with this diagram that we have a question. We have the retrieval phase that we retrieve document, and based on these documents that now we understand can be produced from out-of-the-box embeddings, put inside a VectorDB, we can actually tune them and improve them and boost business KPI. Let's say, like we saw in the app market, we want to boost install rate. So by training embedding space based on app that was searched them and what was installed, I actually boost business KPI, and this is what we eventually see in the A/B test. We improve these KPIs, okay? It's very straightforward. I think, so this is one of the go-tos, so we can fine-tune. We don't need to fine-tune all the time. Sometimes out-of-the-box models are good enough, but in order to know when it's good or not good enough, we need an evaluation process. And evaluation processes, it's something that usually people that are not data scientists tends not to do. And we encourage you to have the sanity check, have some process that can evaluate and A/B test whatever you're trying. And that's it. Questions?